Hello everybody, hope you're all well. So you should have gotten a copy of the initial handout here, and you'll see that essentially what we're going to be doing is taking a rectangle of length 8 and with 3 here, and we're going to rotate it around this axis like this, so it goes around in circles in particular, okay? This is a topic that is covered in calculus known as solids of revolution here, so we're just doing a very basic idea from that. So we wanted to determine, we're going to create, so notice that when you do this, you're going to create a solid of some sort, and I'd like you to calculate the volume of the solid. So I guess the first thing we want to do is take a look at what the solid's going to look like here. So we can sort of visualize something like this here. You'll see that, you have something that like this, and the same thing is going to happen down here. Now, your intuition should tell you that we're going to get a cylinder. Standard right cylinder, circular cylinder. But of course, we want to make sure that why this is the case here. Now, we know it's going to be a right cylinder, right? We can determine this because it's a rectangle, so all the angles here are going to be right angles. So as a result, we can see here that this upper line here, this upper side, and the vertical side here are perpendicular. This upper side is going to be turned into a base. The lower side is going to be turned into a base as well. So you got two right angles here. That should work out really well. Furthermore, we know it's a circular cylinder because this 3 is rigid. This side length of 3 is going to be rigid. It's going to go all the way around like this, which means that this point over here is going to trace out something that is always going to be 3 units away from this central point here, which is the definition of a circle here. So as a result, we're going to have a circular cylinder. It's also going to be right here. Now it's a right circular cylinder, so we know the volume. We can calculate what that is. The volume is going to be pi r squared h. Now, very luckily, we now know what we have here. So the 3 represents the radius here, so it's going to be pi times 3 squared, and the height here is going to be 8. So in this case, it's going to be pi times 9 times 8, which is 72 pi, right? So that's going to be our rectangle. Now, of course, you don't have to use a rectangle. You can use other things as well. It doesn't have to necessarily be this. For instance, if we did something like this here where we use a right triangle instead, we can do much the same thing here and create something like this. Well, note that we have a bottom side here. So first off, this whatever solid this is going to look like here is going to be, again, a right solid here. You have a right angle here. This is going to be sort of the axis of the solid. This point remains on its own here. So that means essentially what's going on, that point is going to remain a point here. This bottom side behaves much like the bottom side of this rectangle over here. So it's going to generate a circle like this. And it would seem that we get this rather strange looking cone-shaped object here. And indeed, what we have here is what we know as the cone. So if we look at the rest of the notes, you'll see that cones look a lot like this here, and things that are not cones that look like this here, so you can see what we have with this. So a couple things you'll note about cones is that all of them seem to have a single point on top. All of them have a single apex on top here. So you have an apex like this here, and there's a single base like this. So, you may have noted last time when we looked at cylinders, the cylinder was sort of the non-polygonal version of a prism. So in a way, we can do the same thing with the cone as well. So, if I may use an analogy, you can think of the cylinder to the prism as the cone would be to the pyramid here. And indeed, we can come up with a definition. Now, this, normally when you think of cones, you don't think of this thing here, but this actually is a cone. This base here is non-polygonal, and it does have a point like this here. So our definition, as you can see from the handout here, that a cone is a solid bounded by one non-polygonal base and a single lateral surface that tapers to a point here. So we're going to have a bunch, just like with the prism here, the pyramid here, the pyramid has a single point on top. We're going to do the same thing with the cone. It's going to have a point on top here. It's going to have a single continuous lateral surface here, okay? Now, again, most of the time when we deal with these sorts of things here, when you think of right cones, you're going to be thinking of right circular cones, and we're going to look at that here in our next video. So we can use this here, but just letting you know that this is also considered a cone, but we're not going to be looking too much at this. Furthermore, also another thing about this is that this cone here, you can see this cone is not the axis. If you connect the vertex all the way to the base, again, it's not a right angle here, so this is an oblique cone. We're really not going to worry too much about those because those are a little bit more complex. We're just going to focus on the right circular ones because those are easier to deal with.